This is our last new material before our first exam, and in this section we're going to go over three types of problems: direct variation problems, inverse variation problems, and joint variation problems. Let's begin with direct variation problems. If x and y are related by an equation that is something of this form where you've got the output variable equals some constant k times the input variable x raised to the nth power, where n is also some constant, then we say that this relationship shows direct variation, and specifically y varies directly with the nth power of x. And since k is a non-zero constant in this equation, we could choose to isolate k by itself by dividing both sides by x to the n, and that would give us the equation that k is equal to y divided by x to the n. So if we're asked to solve a direct variation problem, we've got a few steps. First, you identify the input x and the output y. Generally, some information about these will be given. Determine the constant of variation. The constant of variation, that's our k value. And in this case, you might need to solve the equation that you've set up to find the value of k. Once you find the value of k, write out the equation for this relationship, y equals k times x to the n. If you're writing this out at this step, you'll know what k is, you'll know what n is, x and y are just variables. And then if you're asked to find the value of y for a different value of x, you would then substitute those values into the equation to find the unknown. So let's look at our first example. We have that the quantity y varies directly with the cube of x. This is our key phrase. So based on this word description, we can write an equation. Since it says it varies directly, that tells us it's of some form y equals k times x to the n. Now we don't know the k from this description, but we will be able to find the n based on how they describe the power to x. And specifically they say the cube of x. So that means the exponent on x is 3 in this case. So we know that this relationship follows this equation. Now more information is given. They give us an xy pair. They say when x is 2, we know y is 25. So remember, you're given an input and you find the corresponding output. Then they ask us to find y when x is 6. So given a next x value, find the value of y. But the only way this function relationship works, where if you give an x value you get a y value, is if you substitute for an x value here, you'd also have to know the k value in order to multiply by this relationship and end up with a y value. So notice we can't find the second part of the expression yet because we're missing the k value. So instead, before we can go directly to our goal, we've got to stop by the information they gave us before, because this xy pair, notice if I rewrite the equation, y is now taking the value of 25, x is now taking the value of 2. Do you see that I wrote an equation that was originally in 3 variables, now down to a single variable equation? And when you have a single variable equation, you can always solve for the missing variable. So here we can solve for k. This simplifies 25. 2 cubed is 8, so this is 8k. Get k by itself by dividing both sides by 8. And we get k is 25 over 8. Now we can use this. So this was our step 1, we identified the input and output. Step 2, we just solved to find the constant of variation. Step 3, let's write the equation. So y in this case is specifically 25 over 8 times x cubed. So then step 4 would be to substitute the known values. Our known value is x is 6 into the equation and find the unknown. Simplifying this with our calculator, and we would get y equals, the corresponding y value for x is 675 when x takes on the value 6. So just to draw our attention, a few key phrases here, as we were told the variation was direct, so we know it had to fit the model y equals k times x to the n. They told us what the exponent on the x should be based on how it was described. We were given 1 point that allowed us to isolate in the equation to find k, and they were given our second input value so that we could substitute that in our now clarified equation to get the corresponding y value. Now our next example is going to be somewhat similar. It's inverse variation problem, so a lot of the stuff is the same. The only difference is instead of having y equals k times x to the n, we now have y equals k divided by x to the n. And this is shown by inverse variation. So our key phrase here is y varies inversely with the nth power of x. That tells us we should set up the equation y equals k divided by x to the n. And specifically in this equation, if we wanted to isolate k, we would multiply both sides by x to the n. These would cancel, and we would get k is just equal to x to the n times y. And see that this is something you could memorize, but it's also something that you could use algebra to solve for each time. We don't really need to memorize this equation because we could isolate k here using algebra if we just knew the inverse variation equation. Now the steps for solving an inverse variation problem are very similar to those for a direct variation problem. In both cases, step 1 is to identify the input and output, find the constant of variation k, and then use this constant of variation to write out a clear equation for the relationship described in that problem, and then substitute known values into the equation to find the unknown. So let's look at our first example with inverse variation. So it says a quantity y varies inversely with the square of x. Now why don't you take a minute to pause the video and give a guess of what our equation would be that's described by this statement. So the key things to pay attention to here is it says inversely, so I know it's going to look something like this. I just have to now translate what the exponent on x would be, and they say the square of x, which square makes us think of x to the second power. So specifically for this problem, it's y equals k divided by x to the second power. So that's our general equation. And notice here we're given a point, x equals 3, and when that happens, the corresponding y value is 8. So what that means is whenever we plug in x equals 3 into this equation, the whole right side becomes equal to 8. And then we're asked to find y when x is 4. So a new x value, and we're asked to find y. Now if you remember, there was something very similar to what we did in our first example. Though we started with different equations, the process is going to be similar in that we substitute to solve for k. So right now your goal is to substitute a given xy pair and solve for k. So I think this would be a great time for you to pause the video and work on this first step that I outlined here. Unpause to check your work. So here in our equation, y equals k divided by x squared, we can replace a few things. For instance, we know y takes on the value 8 when x takes on the value 3. This equation could be simplified. 8 equals k divided by 9. Now our goal is to solve and find k. So we're going to multiply both sides by 9, and we would get k is 72. So we found the constant of variation, which means I can improve my original formula. Y is specifically 72 divided by x squared. So then we write our proper equation. And now, given an x value, we can find a y because notice the right side only has a single variable left. And whenever you've got a single variable on one side, you can substitute and find the remaining value. So we have y is equal to 72 divided by 4 squared. Typing this into our calculator, and we would get y equals 4.5. Now, joint variation problems build upon our last two concepts. The main difference with joint variation problems is that in the same equation, you have both direct and inverse variation. So it's kind of combining the ideas of our previous examples into a single problem. So for joint variation, it occurs when one variable varies directly or inversely with multiple variables. Specifically, we have x varies directly with both y and z. That would give us the equation x, which varies directly with y and z, equals some constant times y times z, because we know we're varying directly, and notice there's no exponent mentioned for y and z, in which case it's implied the exponent is 1. Another example is that x could vary directly with y, so it's varying directly with y, but inversely with z would yield this equation, x equals k times y, all divided by z. And one thing to note is that in a joint variation problem, you only use one constant, k. So it's not like the direct and the inverse relationships have their own constants, it's just a single constant for that equation. Now here we've got our next example. X varies directly with the square of y and inversely with z. Now we've seen a few examples where we take a word description and we translate it into an equation for joint variation. So why don't you take a moment to attempt that on your own? Try to translate this word description into a joint variation equation. Pause the video and then unpause to check your work. So let's take this piece at a time. The idea that x varies directly with the square of y. So the square of y makes us think of y squared. So we have x, since it's direct variation, it's going to be the constant times the variable. But since it says inversely with z, that means you divide by z, so this whole thing is getting divided by z. So we've translated our word description into a joint variation equation, and then we're told if x is 40, when the inputs of y was 4 and the input of z was 2, so these taken together, along with our equation, would give us an x value of 40. Then we're asked to find the new value of x when y is 10 and z is 25. So in this case, the procedure is going to be the same as before. Substitute the known values so that you can isolate k. Once you find the exact value of k for this situation, then rewrite your equation with more specific terms with what the k value is, and then substitute the new inputs to find the corresponding output of x. So let's start solving for k. So in our step 2, we are going to substitute these values into our equation to solve for k. So we were told x was taking the role of 40. We don't know k, that's what we're looking for, but we know y took on the value of 4. And we know z takes on the value of 2. So I'll make that clearly a 2. This equation would simplify to 16k divided by 2 equals 40, which we could have 40 equals 8k. Dividing both sides by 8 here, and we would get k is equal to 5 in this case. So our more specific equation, we know in this case, k takes on the value of 5. So we've got our exact equation, x equals 5y squared all divided by z. And now we substitute in our known values. Y is 10, z is 25, so we get x equals our k value of 5 times 10 squared all divided by the z value of 25. Simplifying this in our calculator, and we would get the x value of 20. So that's it for these 3.9 notes. Be sure to do our textbook homework problems, which are listed on Canvas. Check each of your answers in the back of the book after you complete it. Remember, they're odd, so you can always check your work. And if you have any questions about it, be sure to reach out via Canvas or PSC email, and then take the 3.9 quiz and prepare for our first exam, which you can see listed in our Canvas module for this week.